Hey, my name is Griffin Price, and this is my Lab 1 constant velocity presentation. So, an introduction to the presentation. The purpose of this lab is to compare two different models, right? An observed model and a predicted model. What we are doing in this is we are comparing data, and the data is a predicted distance over versus time. From an object with a constant velocity, a moving object with a constant velocity, right? The models in Newton's second law. So there were two models. We used two models, an observed model and a predicted model. The observed model we used was by videoing the object moving and using a video analysis program called Tracker to track its distance and the time to calculate its constant velocity and give data points, and that's given in the orange line to the right. And the other model was a computer coding model used through GlowScript to predict the same data, the distance and time that this object was going in its constant velocity. And Newton's second law, which is F equals m times a, this is all kind of built around that law. And I'll explain on the next slide that. And as you can see the graph there, that's a brief glimpse at what I came to, what the data shows. So the main physics, like I already said, Newton's second law, it's the big equation, F equals m times a, force equals mass times acceleration. This experiment wants to kind of think, it wants to get you to think about it like, okay, how is this mass going to, alter? Will it? The answer is no. The mass really doesn't change of any object unless you cut it in half. How is it acceleration? How is that altering? Is there even acceleration? And the answer to that is no. It's a constant velocity, so there's no acceleration. And it really wants you to think about the forces at hand, which you can think about for days. There's so many different forces, that you can think about for one object. So that's quite interesting. Now, the really important one that we really want to know is the kinematics equation, which is the equation on the bottom there. Final position equals initial position plus initial speed times time plus 1/2 acceleration time squared, right? So basically this equation is trying to find how something goes from this position to the next position, given its speed and acceleration and all that. And basically, we already know this has no acceleration because it's at constant velocity. So that whole portion to the right is zeroed out, and now you're really just looking at initial position plus its initial speed, which is its constant speed. So let's talk about some initial conditions. Well, we know that the system and its surroundings, particularly my system, was in the physics lab classroom that we usually have. We have a track with a cart on top of it. So I use that cart as my system. And the surroundings being everything else, the track that it lays on, the table that the cart and track is on, the floor that the table's on, the roof, the air, me recording the video. It's all part of the surroundings. Total time of the video, I knew I wanted it to be approximately 1 second long, so I made it around that. I knew there was going to be a constant velocity based on what the lab instructions said, and I knew its initial position already. I was going to start the video at 0, 0, and yeah. So experiment and discussion. So first of all, let's talk about the experiment, the video analysis. I used the program, the software Tracker. It worked beautifully. It analyzed the video and it gave me a set of data points, and it gave me its own graph. I did not include that graph here. I put the graph that it gave me with the next model, the computational model or the predicted model, and let me explain that. So there's the code to the right, the code that I changed. So ball position, 0, 0, 0. Ball vector, or the ball velocity. So I took its initial velocity, which is also its average velocity. I took its average velocity and I made it 0.0163. That's what the average velocity was in the x direction. Okay, delta t. When I used Tracker, it gave me increments of 1/30th of a second, so I used that for the same. The total video was around 0.9 seconds long. There was no net force. There was no update on velocity because it was constant, and the position updated with the velocity of 0.0163 in the x direction. So let's think about this. Were there any error? Yeah, of course. Air resistance and friction. You know, those could lead to some discrepancies that I didn't code for. What if we went the opposite direction, in this case, the negative x direction? Well, I don't think it would be that different. The velocity would still be the same. It would still go the same distance, just in the opposite direction, right? And how many pushes and pulls to get F net to be 0 on the system? Well, there's gravity, you know, there's friction, there's air resistance, and there's also momentum. So that probably what makes it 0. Thank you for your time, guys.